All right, so let's look at question number 4. So here in question number 4, we've got May leaving Mr. Bywater's classroom to get a drink of water from the water fountain. All right, you can read the problem. I'm not going to take too much time going over that. What I would like to look at is that it says assume away from the classroom is in the positive direction. So let's assume that May starts here. This is Bywater's classroom. All right. So what's happening here? She is going to the 8-meter distance, which is taking her 10 seconds, right? So she's going in this direction. Okay, so I'm not doing a formal motion map here, but I'm just going to draw a picture that shows basically the idea of what's happening. So she goes 8 meters, and it takes her 10 seconds to do that. All right, then she's here at that 8-meter point, and she stays there drinking water for 5 seconds. And then she turns around and she goes back the opposite direction. And this time she does the 8 meters in 3 seconds. All right, now you could draw that as a motion map if you wanted to, and I saw a lot of people doing that in class, may find it helpful. Okay, but right here, we're just going to see if we can answer each of the questions. First, find the distance traveled by May. And remember, distance is the full distance that's traveled, so we follow the whole path. So in that situation, we said that she's going 8 meters this way, and then she goes 8 meters back to the beginning. Now, if that's the case, that means that her whole distance there is 16 meters. 8 meters one way, 8 meters back the other way. That's the distance. All right. Letter B says find the displacement. The displacement is the change in the position. Okay, the change in the position is from the starting point to the ending point. What's the distance between those two? Now, in this situation, the starting and ending point are both in the same place. What that means is that the displacement is 0 meters. It doesn't matter what happened in between that initial and final position. All that matters is that the initial and final are both 0. All right, that they both start and end in the same place. All right, next we move on to May's average speed. Now, average speed is the total distance divided by the total time. Now, we already found the total distance. The total distance was 16 meters, right? And then the total time is the total time. It does say for the whole trip. Okay, so she's got 10 seconds that she's moving, and then she's got 5 seconds where she's at rest, which is still a speed. It's a speed of 0. And then she's got 3 seconds that she's going back to the classroom. So the total of that, 10 plus 5 plus 3, is 18 seconds. If we add all that together, we go ahead and divide, and you should get about 0.89 meters per second. All right? And that is the average speed. Now we're looking at average velocity. Now, average velocity, looks like I'm going to need a little more space here. So average velocity is total displacement divided by the total time. Now this, sometimes we just write as delta x is our displacement, the change in our position, divided by the total change in time. And in this scenario, the displacement we found in letter B was 0. So 0 meters is my displacement. The time is 18 seconds for the whole trip, but of course it doesn't matter because that means that my velocity, I'm going to put a vector on top of that, just like I should have put a vector on top of the x there. My velocity is 0 meters per second. And sometimes students find that confusing to say, but she was moving. Yes, but remember, velocity has a direction with it. The only reason I'm not writing a direction here is because it's 0. 0 doesn't have a direction. You can't say 0 to the right. That's 0 to the left, or 0 up, or 0 down. It's all 0, so it's fine when it's 0 to just say 0. Okay, but you've got vectors going to the right, right? You have all these vectors going to the right, and then you have vectors going to the left, and when you add those vectors together, they add together to give you 0. And so yes, the direction matters. The average velocity is 0. On average, I accomplish nothing because I'm in the same space that I started. Okay? Letter E is find May's maximum instantaneous velocity. Now, instantaneous velocity is basically the same thing as instantaneous speed. So the velocity, instantaneous, is equal to the speed, instantaneous. Okay? Except, of course, the velocity is a vector and has a direction. So what I'm going to do is I'm going to find out how fast she's going at each of these scenarios, right? Up at the top, I know that she was going 8 meters in 10 seconds, which is 0.8 meters per second. At rest, she went 0 meters in 5 seconds, so that's 0 meters per second. And then the speed down here at the bottom, she went 8 meters in 3 seconds, which is 2.6 repeating, or 2.7 meters per second. And you can see that the fastest, the maximum velocity would be this guy right here. All right. Now, of course, because it's velocity, we need a direction. And so the direction, it does say that away from the classroom is positive, and so therefore she's going back towards the classroom, so this is negative. So the answer to E is and if I round it, 2.7 meters per second, and then you can either put a negative, or you can say 2.7 meters per second at 180 degrees, or any of the other ways that we talked about talking about a direction there. All right, so that's number 4. I hope that was helpful. Let's go on to number 5.